Are the slides visible?
Yes,
Yes,
sir.
sir.
Visible.
Yes,
Visible.
sir, visible.
Right. So now let's move on upon the further information about crystal structure. The terms polymorphism or allotropy. It is said that some metals as well as non-metals may have more than one crystal structure, and this phenomena is known as polymorphism. The same phenomena, when it exists with elemental solids, it is known as allotropy. So if you have uh, an alloy having more than one crystal structure, you refer to it as polymorphism. And when you have elemental solids having more than one crystal structure, you refer to the phenomena as allotropy. For instance, the example of carbon. Carbon, depending upon the temperature and external pressure, could have the crystal structure in the form of graphite, which is a stable polymorph at ambient conditions, that means room temperature and pressure, whereas same carbon, which is an elemental material, could have an allotrope, which is known as diamond, and it is formed at extremely high pressures. That means a different crystal structure known as diamond, which is being formed at higher temperatures. So you should have an understanding of the fact that materials could have different crystal structures uh, for the same chemical composition, and this dependency of crystal structure is dominated by the temperature and the external pressure. So if you vary the temperature or the external pressure, you could have same material having different crystal structure. For instance, the example of carbon, or if you consider steel, which is an alloy, steel has BCC crystal structure, body centered cubic crystal structure at room temperature. The same steel could have an FCC crystal structure if you raise the temperature approximately above 800 degrees centigrade. We'll look into this in more detail later on when we look into phase diagrams, but for now you need to understand that the same material could have different crystal structures depending upon the temperature and external pressure. Clear enough?
Yes,
Yes,
sir.
sir.
Yes.
All right. Now, moving on towards crystal systems. Crystal systems basically define the geometric arrangement. It says that there are many different possible crystal structures, and it is convenient for us to divide them into groups according to the unit cell configurations or atomic arrangements. We'll focus primarily on unit cell configurations at the moment. Based on the unit cell geometry and without regard to the atomic positions in that geometry, we can divide the crystal systems into seven major crystal systems, and these crystal systems are defined by the dimensions A, B, and C, and the angles alpha, beta, and gamma. That means the complete geometry of a crystal system can be defined by these six lattice parameters. Lattice parameters A, B, and C, and the angles alpha, beta, and gamma. For example, if you talk about cube would have same dimensions, that A would be equivalent to B would be equivalent to C, and alpha, beta, and gamma would essentially be 90 degrees. So this is the configuration of lattice parameter for a cube. You have several different options available, or several different geometric arrangements are also possible. Now, if you talk about A, B, and C, A is the length along the x-axis, B is the length along the y-axis, and C is the length along the z-axis. Similarly, alpha is the angle between YZ plane, beta is the angle between x and z axis, and gamma is the angle between xy axes, and it is on the xy plane. So these six lattice parameters, the dimensions and the angles, they define the unit cell geometry. Now, you should know that this is the geometric configuration. You have cubic, you have hexagonal, tetragonal, rhombohedral, orthorhombic, monoclinic, and triclinic geometric arrangements defining the crystal systems. Within this cubic system, you could have FCC, you could have BCC. FCC and BCC basically they define the atomic positions. These crystal systems, seven crystal systems, they are without any regard to the atomic arrangements. But they can further be divided into FCC and BCC depending upon the atomic arrangement within this cubic unit cell. For your purpose or from the point of view of this course, since we are focusing on metals only, you would be interested in cubic geometry and in hexagonal geometry only, because metals normally follow either the cubic geometry or the hexagonal geometry. They could fall in the domain of FCC, BCC, or they could fall in the domain of HCP, which is hexagon close packed crystal structure. I hope this is clear to you.
Yes, sir.
All right, moving on. The important aspects that would be looking into are crystallographic directions and crystallographic planes. How do you identify a direction in a unit cell, and how do you identify planes in a unit cell, and how do you represent them? So we'll be looking into crystallographic directions first, and probably in next week we'll start with crystallographic planes. So in order to uh, find the indices, when I say indices, indices represent the direction, specific direction. In crystallographic directions, you represent the direction by three indices U, V, and W. These three digits basically specify a certain direction in a crystal system, and they are represented in square brackets. So a direction in a crystallographic system is represented in square brackets with three indices U, V, and W. Now, how do you find out U, V, and W? U is basically the amount you have to travel along the x-axis. So U basically is representation of movement on x-axis. V is representation of movement along y-axis, and Z is essentially the movement along the W is essentially the movement along the z-axis. Now let's say if I have this vector which is starting from this origin and is ending at the half of the length along the y-axis. The first thing in order to find out the indices of direction is to have the vector passing through the origin. So it says that a vector of convenient length is positioned such that it passes through the origin of the coordinate system. For example, in this system, it is this O which defines the origin, and the vector is passing through the origin. Let's say I have changed my origin and I decide that my origin starts from here Z, Y, and X. So I have to move this vector in a way such that the parallelism is not disturbed and it still passes through the origin. So I'll move this vector this way so that the vector starts from the origin, the newly defined origin O dash, and the parallelism is maintained. So whenever a direction is given to you to find out its indices or its directional indices, you have to make sure that the vector is passing through the origin, or you can move the vector in a way such that the parallelism is not disturbed and the vector starts from the origin. Now, if this first condition is being satisfied, we'll now try to see the movements along x, y, and z axis. And we say that for a unit cell, this unit cell, the whole length is represented by 1. The whole length along the y-axis is represented by 1. And the whole length along the z-axis is represented by 1. So if I have to find out, if I have to find out the movement along x, y, and z axis for this green vector, and this is my origin, how much do I have to move along the x axis so that I get to this end point? How much do I have to move along the x axis in order to get to the end of this vector?
Sir, 1 by 2.
Yes, along the x-axis I will have to move 1 by 2. How much do I have to move along the y-axis?
1, sir.
1. And how much do I have to move along the z-axis?
0.
0. Now, once I have found out these projections or the movement along the respective axes, I have to reduce them to the smallest integer values. How do I do that? I multiply every value by 2. Movement along x would become 1, movement along y would become 2, and movement along z would become 0. And this 1, 2, 0 would be my direction for this vector, which is placed in the square brackets. So the three indices not separated by commas are enclosed in square brackets. This would give me the direction of this vector shown in green color. Is this clear to you?
यस सर सर ये अगेन सर ए बी और सी जो हैं इनको हम 1 कंसिडर करेंगे ना
The complete unit cell
तो
from
सर
the origin to the
तो सर वो जो
edge of.
हेक्सागोनल होगा तो फिर उसके लिए
We'll come to that. We'll come to that. Don't worry
ठीक है
about
सर
it. Hexagonal mein we'll come to that. So far, is it clear?
Yes, sir.
All right. Now moving on, there are certain things that you need to know about the crystallographic directions. That means for each of the three axes, there will exist both positive and negative coordinates. The negative indices are also possible, which are represented by a bar over the appropriate index. So if you have to represent the movement along the negative direction, you would represent it by a bar on top of the integer. For example, 1 bar 0 direction would have a component negative in the negative y direction. Clear enough? This 1 bar would represent the movement in the negative y direction.
Yes, sir.
Third thing is also changing the sign of all indices produces an anti-parallel direction. For example, 1 bar, 1 bar, 1 bar is directly opposite to triple 1 direction. For instance, 1 bar, 1 bar, 1 bar is essentially this direction. This is 1 bar, 1 bar, 1 bar direction. An exact opposite direction would be in this negative direction. Obviously, it is in 3D, so you would have to make use of your imagination. 1 bar, 1 bar, 1 bar would be an exact opposite direction. I hope this is clear to you. Another important thing is that if more than one direction is to be specified for a particular crystal structure, it is imperative, it is important for maintaining the consistency that positive negative convention once established is not changed. That means if you have made the positive, negative x, y, x, and z axes, don't change the convention or origin if you are having multiple if you have to identify multiple directions within the same crystal structure. This is for the easier convention. Now, if you have to draw the following direction within a cubic unit cell, which is 1, 1 bar 0, how would you do that? Let's say this is my origin. So I have kept my origin as same. I would have to move how much on the x-axis? 1 unit, which is that of complete unit cell. And then I'll have to move in the negative y direction, complete 1 unit. Since the movement along z-axis is 0, this would be my direction, which is known as 1, 1 bar 0. Clear enough?
Yes, sir.
All right. Moving on, there are certain things that you need to know that for some crystal structure, several non-parallel directions with different indices are crystallographically equivalent. That means the spacing of atoms along each direction is the same. For instance, I have this cube with me, and let's say this is a a BCC crystal structure where 8 atoms are there at every corner, and there is one atom within the center. Now, my positive y direction is this, my positive x direction, z direction is this, and my positive x direction is this. If I say the direction, if I have this direction is essentially 1, 0, 0 direction. Similarly, if I have this direction is essentially 0, 1, 0 direction. Or let's say if I have this direction, it is essentially 0, 0, 1 direction. Now, if I see all the three directions, do they have same lengths? Since we are talking about a cube.
Yes, sir.
Yes.
And the atoms situated on this directional vector, the distance between this atom number 1 and atom number 2, the distance between atom number 1 and atom number 3, and the distance between atom number 1 and atom number 4, is this same?
Yes, sir.
All
Yes,
right.
sir.
So it means the spacing of atoms along each direction is same. That means 100 is equivalent to 001 and is equivalent to 010 directions. These are crystallographically equivalent directions. Clear enough?
Yes, sir.
Yes.
All right, so it means in cubic crystals, all directions represented by the following indices are equivalent. 100, 1 bar 00, 010, 01 bar 0, 001, and 001 bar. They are crystallographically equivalent directions. And in order to write these 6 directions separately, you can represent them into a family of directions, which is represented by angular brackets and having the indices 100. So this would mean that I am referring to all these 6 directions. Clear enough?
सर ये पॉइंट रिपीट कीजिएगा एक दफा.
What I'm trying to say is that I've said that these 6 directions are crystallographically equivalent directions. Clear?
Yes, sir.
Now, in order to write these 6 directions separately, I can refer to them as the family of directions. And how do I represent that family? I represent that family in angular brackets having the indices 1, 0, 0. Clear?
Yes, sir. Clear.
All right. Now,
सर
G.
सर इसमें आप कोई भी इंडेक्सेस लिख सकते हैं ना, 001 भी लिख सकते हैं, 010 भी लिख सकते हैं.
Normally, this convention is used, and this convention means that I am talking about all the 6 directions. Normally, this convention is
sir.
used. All right. ठीक है?
Okay, sir. Thank you.
All right. You're welcome. So, furthermore, it says that directions in cubic crystals having same indices without regard to order or sign. For example, 1, 2, 3 or 3, 2, 1. They are crystallographically equivalent directions. So if you have 1, 2, 3, or if you have 3, 2, 1, or 1, 3, 2, or 1 bar, 2, 3, they are all crystallographically equivalent directions in cubic crystals. Clear?
Yes, sir. Clear.
All right. You can try it yourself, draw the 2 directions and see the number of atoms sitting on that direction per unit length. And you would love, and you would come to know that they are crystallographically equivalent directions. That means the spacing of atoms along these directions would be same. Moving on to the difficult part, which is hexagonal crystal structure. Now in hexagonal crystal structure, there are 2 representations that are being followed. For hexagonal crystal system, it is more convenient to use 4-axis coordinate system. That means you would have 4 indices U, V, T and W. This is one convention that is being used in hexagonal crystal structures where A1, A2 and A3 are the axes on the basal plane. A1 is essentially positive direction of this axis. A2 is positive direction over here. A3 is positive direction over here. And this is the Z direction. All right. So you have 4 indices U, V, T and W. And they are representing movement along A1, movement along A2, movement along A3 and movement along Z axis. Clear enough?
Yes, sir.
All right. Now this is one convention that is being used. For example, let's say I have this direction. This is my origin. And I have this direction shown starting from the origin going till the end of the hexagon. All right. Now, in order to define this direction, I have U, V, T and W, which is A1, A2, A3 and Z movement. How much do I have to move on A1 axis? For this direction, how much do I have to move along the A1 axis?
Sir, 0.
Along A2,
0, sir.
along A3
Sir, वो भी 0 है.
and Z.
Sir, 1.
1 point, sir.
So the Miller or the directional indices would be 0, 0, 0, 1 as it is written over here. Clear? Is it clear?
Yes, sir. Clear.
Yes, sir.
All right.
अच्छा
Let's
सर, मैंने
say
आपसे पूछना था कि ये ओरिजिन रखने की फ्रीडम है, हम मतलब पूरे यूनिट सेल में कहीं पे भी रख सकते हैं ओरिजिन?
रख सकते हैं, लेकिन you have to place it in a way that your movement from the origin to the directional head becomes convenient for you in order to find out the numeric uh,
समझ गया सर.
uh, the travel along the axes. All right. आपके लिए ये आसानी हो कि आप आइडेंटिफाई कर सके कि आप हर एक्सिस पे कितना मूव कर रहे हैं. क्लियर?
जी सर.
All right. Let's say I have a direction over here up till this point, from origin up till this point, which is the edge of the or the corner of the second unit cell. इसके साथ एक और unit cell अगर मैं if I could draw it, so एक और यूनिट सेल ऐसा हो मेरे पास कि ये जो है ये इसके एज तक आ रहा हूं मैं. आई एम मूविंग फ्रॉम द सेंटर टू द एज ऑफ दिस यूनिट सेल. क्लियर? दिस इज द डायरेक्शन.
Yes, sir.
U V T W A1 A2 A3 Z. Now how much do I have? I'll move and you will tell me what is the movement along the axes. So for A1, if I start from this point and move in this direction, how much have I moved?
Sir,
Sir.
1.
0.
From A1, if I move in A2 direction, how much do I have I moved? This is parallel to A2.
Sir,
Sir,
one.
1.
-1, sir.
Is it negative direction? A2 is positive in this direction, so I'm moving from here to here. 1 or -1?
Sir,
Sir,
minus
1.
-1. And how much have I moved in this direction?
Sir,
सर
1.
आपकी आवाज सही नहीं आ रही सर.
Are you not able to hear me clearly?
ठीक आ रही सर आपकी आवाज.
Beta, please check up on your internet connection. How much have I moved in the negative A3 direction?
Sir, 3.
यहाँ से यहाँ तक 1 है, फिर
Sir,
एक और यूनिट सेल है.
So it
3.
will also 1.
सॉरी,
सर 1 तो नहीं होगा सर, वो यूनिट सेल के सेंटर तक 1 होगा, देन आपने एक और एज तक का, तो सर 3 होना चाहिए.
3 होना चाहिए. या देखें ना,
सर वो सेंटर तक तो नहीं है ना, आपने उसके कॉर्नर तक.
sorry, this is center. My fault. This is up till this point.
यस सर, फिर 2 होगा.
Or no. For example, just give me a minute. It is still the edge. If you see, I have moved from here to here. How much? 1 U V T W A1 A2 A3 and Z. All right. From here to here, I have moved
Sir,
1 unit.
Yes, sir.
From here to here, I have moved 1 unit. Now
Yes,
from
sir.
this point, how much do I have to move in this direction to get to the edge?
Sir, 2 points.
So that would be +2 or -2?
Sir, opposite है तो -2 होगा.
-2. And how much on the z-axis?
Sir, 0.
So you'll have the indices as 1, 1, -2 bar 0. Clear?
Yes, sir, clear.
Alright, आप
Yes, sir.
यहां से मूव करें, यहां से मूव करते तो फिर आप 3 यूनिट्स लेते. क्लियर? Clear enough?
Yes, sir.
जी सर बिल्कुल.
Alright. Now there are times that you could have 3 indices for HCP also. How do you convert these 3 indices to 4 index system? 4 index system, if you see over here, is shown to you. If you see for 4 index system, essentially the A1, the length along A1 is subdivided into three portions. This is 1 by 3 of A1. This is 2 by 3 of A1. And this is complete one step along A1. Clear?
सर एक दफा रिपीट करें.
If I take my origin from this point till this line, the first line drawn, you have essentially moved 1/3. From origin to this second line, you have essentially moved 2/3. And from origin to this edge, you have essentially moved a single step along the A1 direction. Clear enough?
जी सर, ठीक है.
Similarly, if I talk about the axis A2, this line represents the movement 1/3 from the origin to the line. This line represents 2/3 movement, and the third line, this line represents the complete one step movement along A2. Clear?
Yes,
जी
sir, clear.
Similarly, along the this what do you say, A3 axis, this line represents 1/3 movement. This line represents 2/3 movement, and this line represents the complete one step movement. And you all also have positive and negative lines for the convenience. Clear?
Yes, sir, clear.
And along the z-axis, the point M represents 1/3 movement from the origin. Point N represents 2/3 movement. And this point represents the complete one step movement along the z-axis. Clear enough?
Yes, sir.
Yes, sir, clear.
Great. So if you have three indices given to you, 111, let's say, given to you for HCP, and you have to convert it into UVTW, 4-index system, or the reduced coordinate system. This coordinate system, A1, A2, A3, and Z-based coordinate system is known as reduced scale coordinate axis system. All right. The 4 indices system is known as reduced scale coordinate axis system for HCP. So if you want to convert the normal indices, 3 indices, to reduced scale coordinate axis system, you have this conversion. That means if you have 3 indices given to you and you want to convert it into reduced scale coordinate axis system, you can use this conversion to convert it into UVTW indices. W would essentially, the movement along Z would remain the same. It is essentially U, V, and T that are dependent upon U bar, V bar, that are 2 indices, the first 2 indices. Clear enough?
जी सर.
All right.
Yes,
Let's
sir.
have a look at an example. So let's say if I have a direction which is known as 111 direction, U bar, V bar, and W bar directions uh, are known for you, the common directions that you are familiar with. And you want to convert it into 4-index system for hexagonal crystal system, or you want to convert it into reduced scale coordinate axis system. How do you do that? You just plug in the value of U bar and V bar for U, and you'll get the value 1/3. Similarly for V, you will plug in the value of V bar and U bar and you'll get 1/3. Similarly for T, it is summation of U plus V with a negative sign. This would be 2/3. And W would be same as W bar, which is 1. So now you have converted this 3 indices system into reduced system, which is this. This is reduced axis system, reduce axis system. Clear? Reduce scale
Yes.
coordinate axis systems. Sorry. So now we'll try to plot both using 4-index system, which is reduced scale coordinate axis system, and the normal indices, the 3-index system, uh, to find out the 111 direction or this reduced scale direction. They should essentially be the same direction. So first, let's use the reduced system. Reduced system. In the reduced system, I have these directions. I have in reduced scale coordinate axis system, I have 1 by 3, 1 by 3, minus 2 by 3, and 1 as the indices. So let's try to draw this direction. This is represented of U, V, T, W, or A1, A2, A3, and Z. So let's see if I have to move 1/3 on the A1 axis. I'll have to move from here to here. Clear?
Yes, sir.
Now, if I have to move 1/3 on the A2 axis, where should I go?
सर
So 1/3 is
A2 की
ये
तरफ
सही है line.
All
yes
right. Now I have to move minus 2/3 on the A3 direction.
In
Minus
the
1 by
opposite
3.
direction.
Yes, minus 1 by 3 and minus 2 by 3. 2 steps. Clear?
Yes, sir.
Yes,
Clear.
sir.
And then I have to move completely along one step along the Z axis. So I'll get to this point. If this is my origin, the direction would be this direction. This is 1 by 3, 1 by 3, minus 2 by 3, 1 direction. Clear? In a reduced scale coordinate axis system.
Yes, sir. Clear.
All right. Now keep in mind this direction. I have drawn this direction over here since it was a little messy over here. So I have shown you over there. This green arrow is showing you the direction represented by 1 by 3, 1 by 3, minus 2 by 3, 1 reduced axis system. This is the direction shown to you. Now let's try to draw or use the original coordinates 3-index system and draw it on a hexagon. In 3-index system, you would only have A1, A2, and Z axis. That means UVW system in hexagonal crystal structure, you will have A1, A2, and Z axis only. You will not have A3 axis. Clear? For the 3 indices in hexagonal unit system. You'll have A1, A2, and Z coordinate system. Clear? Yes, no?
Yes, sir.
yes
All right. So if I have to move 111 direction in the 3-axis coordinate system for hexagonal crystal, I'll move one step A1, one step A2, and one step in the Z direction. This would give me the same direction which is represented by the reduced axis coordinate system. Clear enough?
Yes, sir. Clear.
Yes, sir. सर जब हम 4 एक्सिस पे ड्रॉ करेंगे तो हमें भी इस तरह
जी
की सरफेस प्रोवाइड की जाएगी.
obviously in other words can't you draw this अगर आपको ये ड्रॉ करना हो तो आप ड्रॉ नहीं कर सकते.
सर कर लेंगे.
एक हेक्सागोन बनाना है सिंपल. ड्राइंग मेरी जैसी गंदी भी हो तब भी चलेगी. सो यू हैव टू ड्रॉ द हेक्सागोन और इस हेक्सागोन के अगर सेंटर यहाँ पे ले रहा हूँ तो इसको रफली 3 हिस्सों में डिवाइड कर लें. अगर ये हेक्सागोन है आपका सेंटर से A1 के लिए 1 2 और ये तीसरा स्टेप हो जाएगा. सिमिलरली इस डायरेक्शन में है तो 1 2 और ये तीसरा स्टेप हो जाएगा. सिमिलरली इधर है तो 1 2 और ये तीसरा स्टेप हो जाएगा. So you just have to roughly sketch it. your drawing could be as bad as mine. It would not be an issue. All right.
Okay, sir.
सर वैसे ये 3 इंडेक्स
Okay, sir.
सिस्टम 4 वाले से ज्यादा सिंपल नहीं है?
Yes, 4 index system is convenient for you to draw. अभी तो आपके पास 1/3 के फॉर्म में आ गई ना. If you have to move 1/4 or smaller units, तो 4 axis system is would be a little convenient for you to draw, provided you have this in mind, the
ठीक है,
distribution in mind. All right.
सही है.
All right. One more thing. One of you asked me a question regarding the AISI nomenclature. Who was he?